So I want to go back to the original question, which is to study the Gibbs measure, which, if you remember, we can write in two different ways. One is we can write it the original way, e to the minus beta. I've taken this normalization. So this is the original energy. Or we can also factor out some constant terms after the splitting. And bring it to this, minus S over D. And now this is the next order, or modulated energy, with respect to some, sorry, I want to do Kn beta of mu, with respect to some reference measure mu, which is here the equilibrium measure, the thermal equilibrium measure, but we can sort of forget what it is. So it's a probability density of this form, okay? So we have learned some things about this function fn last time. In particular, we learned that fn is bounded from below, uniformly in the configurations, and the bound from below. So remember, I can always I always have to add this in the logarithmic case, and I have a bound from below by minus a constant n1 plus s over d. So, for instance, I can plug this thing inside the definition of the partition function, and it gives me an upper bound for log Kn of mu, which is actually going to be Cn, C beta n, essentially. Because you see, you have n1 plus s over d, and conveniently there is an n minus s over d. So these terms cancel, and then you just get a beta n. Okay, I'm neglecting this thing here. So up to the additive log n. Okay, so this gives you an upper bound. In fact, this is the correct, this is a good upper bound, because we'll see that this is the right order of things. And we can match it with a lower bound. So to get a lower bound, so K is defined like this. It's the integral. To get a lower bound, it's a different business, and there is a quick way to do it, and I will not do the details, but you can do it with Jensen's inequality. So Jensen will allow you to bring the exponent down and compute integrals, and it's not too long. So it's going to give you essentially the same order, again up to additive log n, and there is an extra factor. Okay, we can make C independent of beta, and that's not obvious, provided we multiply by. So there is an extra factor if you want. Log beta, let's say 1 plus log beta when beta is small, and that's in 2D. In all other dimensions, you don't need this correction. So this is a sort of low temperature, low beta correction, so high temperature. Okay. So another way to look at this is actually to think of it in blown up coordinates. So far I've discussed the situation where we have an equilibrium measure that lives in a bounded set. So we have points at distance n minus 1 over d, typically, from each other. And you can look at things in zoomed coordinates, where you're going to multiply everything by n to the 1 over d. You can take a centering point if you want. And now we have a large set of size n to the 1 over d, where the particles are now separated by order 1. Okay, so I'm going to call x prime I the blown up coordinates. You have a question, Jerry? No?
I have a question actually. So it's not the same constant, and it's
no. But one I put a minus and one I put the plus.
okay. So
you can make it the same if you want.
No, but it means that it's really a whole range of.
Yeah, so it's between minus c and c, the whole range. Yeah. You can take the max of the two and make them the same.
Yeah, sure.
Yeah. Was that your question
yes.
as well? Okay.
The question would be whether you expect to have an equivalent of this.
We will have one soon. Yes. So we will have the exact constant that's in front of n. And then there will be remainders of lower order. Okay, so now I want to zoom my system. Assume the origin is in the set, for instance. And we're going to define a blown up measure as well. So mu prime. So there's going to be x prime, mu prime. So the only problem with mu prime is it's no longer a probability. It has integral n with the way it's scaled. Okay, so now you see if the equilibrium measure here was density 1, this thing is also density 1, but it's much more extended. So the total mass is n. And we can define a blown up version of the energy Fn. So now here I don't put an n on purpose because the definition doesn't really use the n in the same way. Okay, so it's again the integral away from the diagonal, and so the only thing to notice here is that, well, there is no n. So the balance happens between this discrete measure that has n points and this measure that now has integral n. Okay. So everything that you were doing before, you can do here. In particular, this renormalization, we can write it in terms of, so there's a 1/2. So I'm going to define electric potential at the blown up scale. There is a square. And I can say that this is equal to this modulo renormalization. So you remember last time I explained how these integrals are infinite, but you can smear the charges. So you smear at the interdistance radius. But for today, now I'm going to, for the sake of presentation, completely neglect the renormalization. Okay, so every time I write an integral grad h squared, it means renormalized. But we don't have to carry this notation all the time. Okay, so this is integral over RD. And what is Hn prime? It's the convolution. It's the potential generated by the blown up charges. Okay? So one of the advantages of zooming is just that it's a more natural scale, because Fn, the original one, it's actually n to the s over d f of the blown up guy, plus possibly, or minus, so I think it's n over 2d log n in the logarithmic case. All right, because you see that when you have two particles, x minus y, if you multiply their distance by n to the 1 over d, you get an n s over d factor. So this is the natural length scale factor. This is why there was always this s over d. And this thing, in the logarithmic case, it's additive, because when you take the log, you multiply by a certain factor, you get an additive term, and so that's where it came from. So now, with this energy, things are more natural, because you see this guy now, f xn prime mu prime, is bounded below by minus Cn. So the only thing that's left is really the number of particles in this scale. And in particular, you can do the same with the partition functions and everything. And what you find is that the log of Kn prime, if you want, of mu prime, that thing is going to be bounded by, in absolute value, by C beta n. So maybe that explains better why I chose to put this multiplier here. Because when you plug that thing in there, this thing cancels out or simplifies, and you just get beta Fn xn prime mu prime. And you also see why there was always this additive term. I told you you should really think of the energy as this plus this thing. They go together.
Yeah, so start from the original.
Yeah.
Is it the only scaling which makes sense? I mean, other scalings are trivial or something?
They're all fine as long as you continue to think that beta may itself depend on n.
Okay.
Okay, so for now I haven't said that beta is independent of n.
Okay.
But you will see that now beta fixed is kind of a natural scale, and you will see it in a result that I will show today or tomorrow. This temperature regime is the one in which the energy and the entropy play at the same strength at the microscopic level. So it's one natural choice. You have other choices, but this is the choice in which...
Okay, whether scale one or the other will be dominant.
Exactly. You don't have dominant part. You have interesting regime where you have competition between energy and entropy. Okay, but one of the, I would say, the flexibility of the approach is that so far everything is beta independent. So the C, as I told you, there may be a log beta that you need to add here. But the C is independent of n and beta, because we want to be able to play with still beta depending on n. Okay? So now you get an immediate, I would say, global law, right? From that, we immediately get some information about the typical size of the energy. So global law or concentration result. Which is a sort of corollary, if you want. The log of the expectation under this Gibbs measure of e to the beta over 2 f xn prime u prime. That thing is also bounded by c beta n. And the proof is very easy once you know all that, because, well, the expectation. So if you think of what this is, you put that inside the Gibbs measure. And now my Gibbs measure, I can rewrite it in terms of beta fn xn prime u prime. And all the other terms are constant, so the additive term, I can just take it out. Okay, so this becomes my new, a third way of writing the Gibbs measure, if you want. Maybe I will do it properly. So dPn beta is also equal to, and here we're going to factor out an n to the n. So there's some normalization again, and here e to the minus beta f xn prime mu prime d mu prime tensor n times. So this is in blown up coordinates. Okay, so the reason to blow up is just it makes things more natural, maybe easier in some sense, and you still have to have a normalization, a partition function. Okay, so now what is this expectation? Well, it's just the ratio of e to the beta over 2f minus beta f divided by e minus beta f by definition. So it's basically k n beta over 2 divided by, I forgot the log, k n beta. Okay, so if you're able to do the ratio of partition functions at different temperatures, you get the exponential moments of the energy. That's normal. I mean, nothing unusual here. Of course, here, this is why I have beta over 2. I cannot have more than beta. And now the log of this, by this relation, I control it. Right? So I control it by c beta n again. Okay. All right, so now if you think of what this is telling you in exponential moments you control a distance between your empirical measure. So I remind you that this function, from what we learned last time, it's a sort of norm squared of the difference between empirical measure and reference measure, right? So with some sense to be specified. And because this is of order n, I mean you have n points, this is a measure of mass n, so in principle this whole thing could be of size n squared. But here we control its exponential moments by n, so we have gained something. Right, so this thing is typically order n. Okay. If I go back to the non-zoomed coordinates, it also tells me or if you prefer, if you had it non-zoomed, would be typically order n1 plus s over d, which is much less than n squared. Okay, so this is why I called it concentration, because, well, it tells you concentration near mu, the reference measure. And this is much stronger than the LDP. I mean, in some sense, it's stronger. If I remind you, last time we saw that we have an LDP at speed n, what was it? N theta. 2 minus s over d, I think. E of mu minus E of mu v. So dp and beta, that you know, the empirical measure is like mu, behaves like that. So this gives you an idea of the size of this quantity, but it's less good than that. Okay, so this is an improvement. The improvement was made possible by the fact that we split and we went to the next order and we looked at the next order term. So we have a more precise description now, because we went from basically a description of order n squared to a description of order n. Okay? If you want, you can control fluctuations of linear statistics this way. Right? If you take a test function, you can plug it with this norm. It will tell you what that you are gaining. Basically, you're going from n to root n. But we will be able to do better tomorrow in terms of linear statistics. Okay, so controlling this f controls some sort of norm. It controls some discrepancy about the points. So when you have your system in now this very large box, right? So you have this very large box now. So if you want to take a sub box and ask, how many points can fall in that box, f is able to control a little bit of this discrepancy, difference between number of points that fall in the box and integral of mu in the box. Control linear statistics, things like that. But so far, we have it at the macro scale. So now the question that I'm going to look into today is to get analogs of this at micro scales, or at least down to micro scales. So we're going to prove local laws. So there's a theorem. And that's going to be, so far it's restricted to the Coulomb case. So I would say we know how to do it in a Rees case, but it hasn't been written up yet because it's quite long and technical. So far it's restricted to the Coulomb case. And it's a paper with Scott Armstrong. And it says the same as this, but in sub-boxes. So you take some cube of size r, and you look at this sort of restriction of the energy in that cube. That thing is going to be bounded by the size of the cube. Okay, so QR is a cube, like this. And what I define by that it's this thing, this gradient of the potential renormalized, but okay, and integrated only in QR. So this is true, I should say, for which R. So there exists a rho beta such that for every r bigger than rho beta, so it depends only on beta, not on n. And rho beta, it's actually a constant independent of anything except maybe dimension. And the max 1 over square root beta. At least in low dimension. And in higher dimension we have some like worse thing. But this is not sharp. So it should be this. It should be this. And for some technical reasons, after d equals 5, we have something less good, but it should be this. And we call that the minimal scale. The minimal scale for rigidity. And you see it depends on the temperature. So this is why we've worked hard at keeping all track of all temperature dependence. When beta is very small, this thing starts to be large. Okay, so it means that you're going to get local loss, but you cannot go too far down if temperature is very small. There is going to be some minimal scale, and the idea is that above that scale, you have good controls in boxes. And below that scale, you expect your gas to actually be Poissonian. So it's like the rigidity only kicks in above a certain scale. So below that, it's not really proven, but you expect Poisson behavior. So of course, the fact that you have to be above some fixed scale, that's normal because you need to at least have a sort of large number of particles before you start to say anything. So if you go below the size where you see no particles, everything becomes kind of empty anyway. So you see, but you can almost go down to r equals 1. I mean, you can go down to r equals some constant, and you have a bound. So remember here, the original one, n, that's Rd. So that's C beta. That's C beta Rd for the largest scale, which in this scaling now is n to the 1 over d. So that's the size of your largest system, n1 over d. That's the macro scale. So we know the thing at the macro scale, and now we're saying it's true at all mesoscales down to this minimal scale. Okay, so how is that going to proceed? It's going to be a rather, I would say it's the most difficult part of everything I've shown you so far, because there's a significant amount of work to do here, because you want to do basically a bootstrap on scales. So you want to take information that you have at the largest scale. So I'm going to write that. Okay, so this goes by bootstrap on scales, a bit like a renormalization method. You start from the fact that it's true at r that happens to be n1 over d. And you're going to try to prove that if it's true at scale r, it's true at scale r over 2. Until you get stuck.
Just one question. At this, I mean, the F measures at this level measures something rough enough that it doesn't really matter whether the shape. I mean, whether it's
whether it's a ball or a square. Or
in some cases, I need something smooth, but at this r to the power d, it doesn't matter.
Yes, 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 indeed. So these laws are relatively rough in some sense. They are not going to be sharp when you look at linear statistics, for instance, of smooth functions. But they
when
are.
I say rough, I didn't really mean rough because it's actually super precise. But I was just concerned about.
Yeah. So the shape doesn't matter, and the other thing is it's optimal. Like you cannot do better. You don't expect better. But it's a certain measurement. What you're taking here is you're measuring in a certain way, which is a very strong norm. So that's why you don't get very good controls, because for a norm that's so strong, you cannot expect. So this was generalized in this was extended to the log case in dimension 1 by my student Luc Pellen. Because so far it's only the Coulomb case, and as I said, we are working on doing the risk case. It's probably going to be okay, but it's technically more involved. But okay, this is already quite some work. So let me explain a little bit the idea, and together with this local law, we're also going to get at the same time an expansion for log k. You know, this thing that's there. So the local laws during the bootstrap brings log k. Yeah. Okay, so what we do to do that, there's two ideas. I mean, two key ideas. One is almost additivity. So we want to show something that's the almost additivity of the free energy over boxes. I'm going to explain more. And the second one is a screening procedure. And the third one, I've already said, it's bootstrap. So the almost additivity is going to come by using two quantities to approximate, let's say, two approximate free energies. One that's subadditive and one that's superadditive. And the screening procedure is going to allow to compare or to show the closeness of the two quantities. I said one that's subadditive, one that's superadditive. Okay. So to define my two quantities, I'm going to define two variants of the energy. Of the energy in a cube. So let me assume I have a cube, and let's assume for For now, I'm going to work with the case where mu prime is constant equal to 1. Okay, so we assume that we have a uniform density of points in this very large domain. It's not a loss of generality, because first we really need to understand that case, and then we will go to the other cases from that case. Okay, so if I have mu prime equals 1, I'm going to define first a function u, which solves my usual Poisson equation that we've seen before. So now I have some points called little n. Minus 1, this is my mu prime, minus 1. Okay, so I can solve this in a cube. If you take a PDE course, you learn that you can solve this with Neumann boundary condition if you want. So given n points, you can define, you can solve this, you can solve that. When is it that you can solve? So that's what I would ask my students in an M2 class. When can I solve this PDE? Yeah, you have an integral condition. The right-hand side.
Your cube is of which?
Any size, cube R. Okay. So the condition is the number of points has to equal the volume of the cube, right?
Absolutely.
Absolutely, you agree, Cedric? Yes.
It's minus 1, or it's the sum of delta xi minus 1?
No, it's the sum minus 1. The minus 1 is not in the sum.
But that's the condition of the 1 is inside the n. N here is the...
Yes.
Well, n is the mass of the Dirac, and and the integral of 1 is the volume of QR.
Yes. You agree or not?
Yeah, it's okay.
N is the number of points here, and this integrates to the volume, right? So the number of points has to be equal to the volume. So this is solvable if number of points is equal to the volume. And what that means really is that basically my cube is neutral. It's exactly neutral. Otherwise you cannot solve. Okay? So if I can solve that, I will define, and I use the same notation. It's not completely, it's not a coincidence. I will define f. How do I define it? So now it's a slightly different quantity, but it's almost the same quantity. Then I will define it like that, with the appropriate constants in front. Okay. And of course, this is to be understood in a renormalized way. So it's like the H before, but the specification here is this Neumann boundary condition. So if you push the boundary to infinity, you recover the same definition as the integral over R2, RD. So that's why it's consistent to still call it F. Okay, now second quantity, I give myself n points again. I solve minus 1, the 1 is not in the sum. And I solve with Dirichlet boundary condition. Now, if you've taken linear PDEs, this is always solvable. Doesn't matter how many n's you have. And you define your solution, you define your energy, G, xn in the cube to be again this thing, but renormalized. Okay. Now, if you had the original guy, the H prime solves the same PDE, right? It solves the same PDE, but doesn't satisfy the boundary conditions. And the idea is that the energy of H in cube R is somehow sandwiched between the two. And this one is going to be sub-additive, and this one is going to be super-additive.
Can you just explain the intuition why the true energy should be somehow sandwiched in between these two?
Okay, there is one inequality that is very easy, I will show you. And the other one is only in retrospect you realize that it will be sandwiched. So, but it's just to give you an idea. So let me show you a few things already.
You have an idea of the V1 is that way you have zero flux, so it's more or less at equilibrium.
So if your true energy, for your true energy, this one doesn't always make sense, right? It only makes sense if the thing is neutral. So that's why what I'm saying is to be taken between brackets. But if you have a neutral guy here, like that, if you look at its H, he's going to have less energy than this one and more energy than that one. I can show it now. Okay, let's do it. So take a solution now to solving. So let's take H solving minus Laplace H equals blah. Same kind of thing in the box, but without giving boundary conditions. You don't know what the boundary conditions are. So the first claim is that this thing, properly renormalized, is always bigger than that guy. Why? Well, you can pose the following minimization problem. Minimize over all h's or all u's such that minus Laplacian u is given. Minimize integral grad u squared in a cube. So it's a minimization with constraint of a convex problem. We should be able to solve that. So what you do, you make variations. You say, okay, I have a class, functions, the Laplacian is prescribed. So I add a harmonic function. That's my only freedom. Right, so you look at grad u plus t phi with phi harmonic. This is going to be always less than grad u squared. If u is the minimizer, phi is harmonic. Expand in t. Do integrations by parts, and you will find that u is constant on the boundary. Okay, but these things are only defined up to constants anyway. I can add a constant, doesn't change my PDEs, so I might as well assume that u is 0. The energy doesn't change if I subtract. Okay, so this one is the one with minimal energy, given the right-hand side. That's just elementary PDE. So it minimizes given the right-hand side. Oh, it's a little computation with Green's formula. But okay, so we have one part of the sandwich. And in addition, this proves that G is going to be good for restriction. G is super additive. Because if I have the union of two cubes, and I have the grad U in the union of the cubes, grad V, the union of the cubes, it's equal to the integral of the first cube, grad V, Q1 union Q2, right? Plus the integral over the second cube. Now you agree, I will lower the energy if I replace by grad V relative to the cube plus here grad V relative to the cube. Because I'm just restricting my problem to a subcube, so G is super additive. Okay, now let's show that F is subadditive. Okay, so here what I want to use is that if I have a vector field in a cube with a given divergence, say this, so this is some vector field, then the integral of grad U squared, so now I'm talking about the U guy, the one with Neumann condition, is always less than the integral of U squared. No, it's the opposite, I want to say. Let me think for a second. Ta-da, ta-da. It's basically a projection property onto gradients. But I have it the opposite way, I think. Where is my projection property? Okay. Whatever. We can do the computation and then we see if it goes the right way. I think it's okay. Yeah, okay. Yes, that's okay. That's where I had my doubt. I want to assume that this one has a E dot nu equals 0 on the boundary. That's what I'm missing. So I want to assume E dot nu equals 0. And then I want to say, this is here, I want to put H, essentially. Okay, so it's L2 minimality of gradients by projection property. If you take a vector field, you can always decompose it into a gradient part and a divergence-free part, right? So the L2 norm of the gradient part is less than the L2 norm of the original vector field. That's the point. It's a very easy point. So we do it by saying E squared. You write it as E as grad H plus E minus grad H squared and expand. Okay, so there is going to be grad H squared. That's good. A positive term. And then a term that's the integral of grad H dot E minus grad H, which you want to integrate by parts. And this is where maybe I did it the opposite way. What did I do? No, it's good. So this one, you write it as a boundary term, H E dot nu minus dH d nu minus H divergence E minus grad H. So these guys have the same divergence. That's the point. Okay, so this is 0 because they have the same divergence, and this has to be 0 if you pick the boundary condition properly. So I guess here I have to pick that dH d nu is also 0. Okay, so you make it so that the boundary term cancels. This divergence term cancels because they have the same divergence by construction. Divergence of gradient is Laplacian. And so you find that this is bigger than that. Okay, so if you want to compute this energy, you can get an estimate from above this time in terms of the energy of any vector field that has the correct divergence. So basically you can relax the condition to be a gradient. You get more flexibility. And this way you show that F is subadditive. So how do you do that? Again, you have your two cubes, Q1, Q2. So you have U in Q1, and you have UQ1 in Q1, sorry. UQ2 in Q2. Q2. And you have the U, you also have the U of Q1 union Q2. In principle, they are not the same. Right? So this one solves with Neumann boundary condition here, this one solves with Neumann boundary condition here, and this one solves with Neumann on the big box. Yes? Okay, so what I do is I let E be the sum of these things. Oh, sorry, I should put a gradient. So I just paste together the two gradient fields. Okay, so paste the gradients. So what happens when you paste two gradient fields and you want to compute the divergence of E? Now this is what I'm interested in because I said I just need to find a vector field that has the correct divergence. So what is the divergence of E? Well, it's the divergence of grad U Q1 in Q1 plus the divergence grad U Q2 in Q2. Plus, in general, you could have some divergence at the interface, right? But du du nu of this one is 0, du du nu of this one is 0. So the divergence of a vector field when there is an interface So it's actually, there is zero contribution at the interface, because the contribution at the interface would be the jump of E dot nu, and that's 0. So it doesn't even matter that they are both 0, it matters that they are both the same. So you now create a vector field where there is no jump of the normal derivative. So no contribution for the divergence. So your divergence is actually what you want. So it's the sum. And here you have the two sets. You have the points that are in Q1, the points that are in Q2. So a corollary of that is that E is now a good competitor for computing the F energy. So by this previous lemma, the L2 projection property the integral of grad u Q1 union Q2 squared is less than the integral of E squared, and that's equal by definition, it's the sum of my two original energies. Okay, so this is the sub-additivity of F. Okay, so what's nice now is we have two quantities which are sub and super additive. Notice one thing is if you have a square like this, a cube, and you solve for this u, Laplace u equals blah, du d nu equals 0. And if you extend it by 0, so if you let E be grad u indicator of the cube, and then outside it's 0, then for the same reason, there is no divergence of E on the boundary. So there is a, you have E dot nu equals 0 here, and E equals 0 outside. So there is no divergence. And so you can solve in the whole space, sum of Dirac's minus 1, in the whole space now. So if you solve this in Q, with that you can build a solution in whole space. And by the same L2 projection property, the true H now, you can bound it above by this energy. So let's say you have an isolated system in a cube of points, and it's neutral, and you solve the Neumann problem on this cube, then you extend by 0. The energy that it generates in the whole space, you can bound by the energy it generates just in the cube. So we call that a screened configuration. So basically, you've screened the configuration when you've managed to make it neutral in a box with 0 Neumann condition. Because from the point of view of the outside, if I sit here, basically it's almost as if this thing is generating no field. Because I can compute the energy as purely the energy in the box. So I don't know if you remember, I told you at the beginning, what we did is we started from a double integral formulation of the energy. We reduced to a single integral in terms of the gradient of the field that it generates. And this allows to start to worry about what's happening just in a box. You don't have to think about all the pair interactions. This point talks to that point, this points with that point. You can just look at the energy in a box. And I told you you can do copy-paste. So that wasn't very clear at the time, I'm sure. But the idea is this, is that if you manage to have only screened configuration as a sort of Lego piece, you can glue together the screen configurations, and you can just add the energies. So now, if I have now a domain, I can sort of cover it by cubes, right? I mean, pave it by cubes. Right, so if I have cubes, Qi, and I solve Neumann problem in the cube, Qi with Neumann condition, then I can do the same. I can let E be the sum. I can paste together all these gradients. And I can compare with H equals the sum of the delta globally. Because this guy has the right divergence and has no jumps of normal derivatives, so it has the right divergence globally, basically. So div E is div grad H. And by L2 projection property, again, take of grad H squared over the whole RD is less than the sum Okay, so if you have screened configurations, you can really use them as Legos. You can paste them, and you can get an estimate of the energy from above. So that will be very convenient, because it avoids having to deal with the interaction between the boxes. So once a box has become very neutral and screened, it becomes effectively sort of independent of the other boxes. You don't have to look at their interaction. And at the end of the day, so this is an upper bound. With the other quantity, we have a lower bound, because the other quantity, you can do restriction. And so that's why I was saying this one is going to be sandwiched, you see, between. So this one is called UI, and this is called VI. So that's trivial. This one is trivial, and this one is the L2 projection property. But you have to be screened. Until you're screened, you're not able to do that. And then the other question is, okay, what's going to be the error in this sandwich? There is an error. And the error, you can guess, is a boundary layer error, because you're solving the same PDE, the only difference is the boundary condition. So if you're in a large box, what you're hoping is the effect of the boundary eventually gets, becomes negligible as you come inside. It's like in a lot of problems of statistical mechanics, right? What you want to do is to understand that in the end, the effect of the boundary decays, and everything is independent of whatever boundary conditions you have put. So this is the work, right? So there will be an error at the end, which is a sort of incompressible error, which is going to be the sum of the boundaries, the boundary sizes. So if you have cubes of size Ri, you will get an error Ri d minus 1. And at our current state, we don't know how to do better than this error. So we can reach the sort of sharp error in that sense. We can show that we saturate at the surface error. But then how to go beyond is much less clear.
What would you like to have?
I would like to have the exact constant in front of the surface term, for instance. Because you see, this procedure is going to give me the expansion of the free energy. It's going to tell me I have a certain term which now is explicit times the volume, the number of points, the volume is the same. So it's the sum over boxes. And then I'm going to get a surface term. Surface term, if you scale it with number of points, is n1 minus 1 over d. And I would want to know, for instance, what is here. And is this term really there? Yes?
So it seems that nowhere in this procedure you really use the fact that all the charges are positive. Or do you use it somewhere?
The screening and the gluing, you don't use it, it's true. You could do with the positive, negative charges. But the point is that as soon as you lose repulsion, your quantities, your F and stuff are not bounded below. They're not coercive. You don't have an equilibrium measure. You lose a lot of things. But this particular idea with boundary conditions, you're right, that is not sensitive to the charges, to the signs of the charges. Do you want to take a break or should we go?
Yeah, question.
Yeah.
To understand. Screening means you need to have n particles in box of volume n, right? There are number of particles.
Yeah, your thing has to be neutral, exactly.
Yes. But I mean, if you have a number of screen boxes, it means a number of conditions.
Yes.
Is that not a problem when you're considering your whole?
Yes, you're completely right. The true configurations will not do that.
Not absolutely.
Okay, the true configurations, they have a number of points that fall in the box. It's not always the volume of the box. You have deviations. So a part of the work will be to show that you can take these true configurations and screen them. So we're going to modify the configurations to make that fall into that category. And we're going to pay an error price for this modification. And so you want, in the end, you show that you make a small error. So this cartoon picture is not too far from the truth. The true configurations are almost screened. We can quantify by how much they are not. So there's going to be a screening procedure. It's going to be an actual surgery, if you want, on the configuration.
In your Lego, the size is given. You don't allow yourself to have bigger Legos or whatever?
Yes, you can pick the size. So as long as you better tile your domain, but you're going to have a choice of the size, and sometimes you're going to want actually to play with that size, yes. So this is for any R. Everything I said is true for any size. But of course, you have an interest in having large boxes, so that your surface errors are smaller, because the more you chop, the more surface you create.
It's a very nice slogan, like Sylvia's Legos game. It looks like a good game for the kids.
Yes, I will try with my kids. I showed my son this morning some pictures of Coulomb points and stuff, and he told me, I don't understand, I already see what's going on. Why do you need to work at explaining it? But anyway, so he's not convinced. Should we continue?
I think it's okay.
I'm ready to roll.
Ça fait toujours du bien, 5 minutes de break.
5 minutes de break? Okay, allez, 5 minutes break. Okay, so I hope I conveyed the idea that you have a sub-additive energy and a super-additive energy. So now what you do is you define sub and super-additive free energies. Okay, so define So by the way, I should say that this idea of doing two or using two quantities, the idea of using two quantities, well, we got it from the theory that was developed by Armstrong and Smart for homogenization, where they use two quantities, and in addition, the fact that they are dual to each other, which somehow here we also have in some sense, but we don't use very much. It's also analogous to apparently something called Dirichlet-Neumann bracketing in spectral theory. So they also use Dirichlet-Neumann boundary conditions. And previously, we had been using these Neumann conditions with Etienne since the work with Etienne Sandier and the screening. But maybe in a less systematic way, we didn't compare it with the other energy. So as we were talking with Thierry, maybe the message is if you have a subadditive energy, it's good to think of whether you can have a second one to work with that would be superadditive. Anyway, so now we have sub-superadditive free energy. So what is going to be? So K would be the one where you put F. So K of Q. So that works only for neutral configurations. Okay, and the other one I'm going to call N, L. And this one is not necessarily neutral. And it's going to have the other energy. Okay, so here I want to put Q, I guess, if I want to respect my notation. Okay, so if since F is subadditive, K is going to be superadditive. So actually log K is superadditive. And here log L is subadditive by obvious integration and separation of variables, etc. Okay, so now what we want to understand is the limit of log K of QR divided by the volume. We want to show that this, as r goes to infinity, has a limit. This limit is going to be called f of beta, because it's a function that only depends on beta now, because when you let the size go to infinity, right, these are cubes that are filled with points. I just take them bigger and bigger. So r disappears, n disappears. And the idea is we have the other one. We think it also converges to the same limit. So this one, because this is super additive, this one is increasing. And this one is decreasing in R. Right, so you have monotone quantities. Okay, so here is your limit. This is f of beta, and so you think that log k is going to go like that. This is log k of qr. This is r. And log L, you think it's going to go like that. So if you can show that they're actually close to each other, So how close can I hope for them to be? I told you there's always going to be a surface error. So if you divide by the volume, the best I can hope for is 1 over R. Okay, C over R. Okay, so if these two are 1 over R close, of course you get a rate of convergence to your limit. So F, so convergence of each to F of beta happens at rate 1 over R. So you have now a quantitative convergence. So that's the advantage of using sub and superadditive quantities, is that you will get this quantitative convergence, provided you can compare the two quantities and show that they are actually close.
Do you improve this rate, or is this sufficient, the 1 over R?
This 1 over R, this is the best we know how to do for now. And it's actually the truth, because there is a boundary effect. There is a boundary effect, it's there. Right? You change the boundary condition, it changes.
Maybe F is closer to 1 than to the other.
That's true. That's true. Yeah. So that's the state of the art, I would say. Okay. So, question, how do you show that these two things are close? Well, we use, that's what the sort of keyword was, the screening procedure. So I'm going to explain with a picture.
Sylvia, can I just ask a very completely silly question? But now you are looking at this limit when R goes to infinity. But at the very beginning, when you talk about the renormalization, you said that you like R to be smaller and smaller, right? So the size of your boxes to be smaller and smaller.
So yes, we lost track of the purpose. You're right. One of the end games is to go down in scales to find local laws. But for now, I'm doing something else. I'm making a sort of detour where I'm actually doing the contrary, going up in size. But now, then I will show you how you use that to go down in scale. Okay, so this is a step along the way. So sometimes you go up, sometimes you go down. Okay, so for now, I'm going up in scales. Okay, so the screening procedure, it's something that we had originally introduced in a work with Étienne Sandier on Ginzburg-Landau, and itself had some roots in ideas of Alberti, Choksi, and Otto. And the idea is you want to take a configuration, and modify it to satisfy, of course, the neutrality and Neumann. And so you don't take only the configuration, you take the configuration plus its potential, right? Its potential V. So this is what you start with. You have a configuration, and you're given minus Laplacian V equals blah, blah, blah. And maybe V is 0 on the boundary. although it doesn't matter at all. You could take any configuration. So the fact that it's 0, we're not going to use. So you're given a configuration in a box. Of course, it's not necessarily neutral. Not neutral in general. You're going to assume you do have some control of the energy on the box. Assume the energy, so what is called our energy, G. We control by something not too bad, maybe CRD, or you can actually accept something worse. It doesn't need to be RD, it could be RD plus 1 or D plus 2, as long as it's a reasonable power. Okay, so you know your energy. In particular, you know your V. If you satisfy a condition like that, we say it's screenable. So configuration should not be too crazy. If it's not screenable, it means you really have a lot of energy in there. And these configurations, you will be able to throw them away because configurations with huge energy have very small probability. Okay, so you throw away, but now you look at the ones that are screenable. And what you want to do is you want to find a good boundary by a mean value argument. You're going to look a little bit inside, and you're going to take a good boundary. So for caricature, I'm going to assume it's a boundary of another cube. That's a little bit inside. That's morally OK. And you're going to keep the configuration inside. So keep config in Qt. And what you are going to know from the fact that it's a good boundary is that E.new, or if you want dv dnew here, is controlled. Is controlled in L2. So the trace of the electric field, if you want, is not too horrible. And you want to delete it outside, so you're going to use the boundary layer. You're going to take your configuration, and you're going to literally delete it. Okay, so everything that's outside this layer. And there is a length scale here, L, which is to be determined later. Okay, so you have your configuration. You want to really throw it away. And then replace it by a new configuration. So only in this boundary layer. In QR minus Qt. Okay, so here it's going to be new. And you're going to do it in such a way that you solve the Neumann problem on the boundary. So in fact, the way to do it is you need to introduce some smaller cubes. Ah, encore le problème du... You see, you have your boundary. You're actually going to chop into smaller cubes here. And here in a cube, you have a given boundary data here. So E.new is given, not bad, but given. And then you're going to solve with 0, 0, 0. You're going to put 0 on all these boundaries and then reach the boundary. So you're going to solve for problems, equations of the form minus Laplace u equals blah du d nu equals something given, which does this. So it's like some function or 0 or 0. And then you want to compute how much energy these configurations have. And so what you plug in here for the points, your points, you want them to be sampled from a Gibbs measure in those smaller cubed. So from a Coulomb Gibbs measure. On smaller cubes with appropriate Neumann data. Okay, so you make mini Coulomb gases in those small cubes, and you make it in such a way that the E dot nu, so the Neumann derivatives, never have a discontinuity and eventually end up at 0. So what this is going to do for you, it's going to re-neutralize the box, because if you look at all the compatibility of the boundary conditions, you will not have a choice of how many points you put in these boxes. You will have to put exactly the right number of points, and in total, the final thing will have the neutrality. And it will have the Neumann condition. Okay, because here you will have 0, 0, 0. So what you need to evaluate is how much energy has been added. Because maybe this new configuration has more energy than the one you had. So the answer is CR, I mean, it's something like that. CRD minus 1L. So you see this is your L. So the volume of this layer is this.
Just repeat the procedure, sorry.
Yes. I'm sorry,
So
maybe.
how can you end up with a neutral gas? So you add this.
You delete everything here.
Everything.
You delete everything, yes. Okay, and now you know how many points you should put to have a neutral gas. Right? So you put those number of points, but you don't do it just like that. You actually decompose into subcubes and throw them from a Gibbs Coulomb gas with prescribed number of points in each cube.
Why do you have to decompose into small cubes, but not just, why do you need several layers of cube?
So actually one layer is enough. Okay. The problem is that because you need to find a good boundary, you need to go quite inside. After one layer, you're done, you're screened, but then you complete, because you want to refill your cube. So that's the reason for several layers. Yeah, but it's because there is first the boundary, the mean value property to find the good boundary. Why you need a smaller? Because that's the size of your thing. So you need cubes to be. You want to work with cubes. You don't want to work with an elongated domain, because that's degenerate somehow. And so this is given to you by the mean value property. You have to go far to find a good boundary. Once you have that, you use that. You can make one. If you, I could present it with just one layer. Okay, with just one layer. So now you solve your. You define if you want a new type of Coulomb gas that has now where you're solving the energy with Neumann boundary data that's non-zero. It's a given Neumann, which is this one. It's this G. It's inhomogeneous Neumann. So that's another Coulomb gas. You can estimate its partition function, etc. So at first, we were doing it by hand. We were just putting the points by hand. But if you put the points by hand, you may sometimes deviate too much from the typical behavior of a Coulomb gas. So if you're only interested in energy minimizers, you can just put the points by hand, like on a lattice. You can put them regularly. But here, it's important to create volume. in phase space. You want to find configurations that have a non-zero volume. You want a certain amount of volume, otherwise they will not weigh in the partition function. So this is what you have to count. You have to count how much energy, not how many, but how much energy you have possibly added.
So your boundary data in, say, in the middle, this one? Not this one. So here, I guess you don't have choices.
Yeah, it's given. And then it's 0.
But it cannot be 0 if the number of points in your small cube is not. So you have this Stokes formula, which.
But yeah, you solve with Stokes. Yeah.
Yeah, so you cannot take 0 everywhere.
No, so here it's not 0.
Here it's not 0.
Here it's 0, here it's 0, here it's 0.
And then the number of points?
So here the number of points compensates exactly.
Maybe it's not an integer.
Huh?
The number of points is an integer, right?
Yes.
And the integral of g on this.
Yeah, so you have to cut, yeah, you're right. So you have to find your, you have to move a little bit your boundaries until you get integers.
Ah, okay.
Yeah.
So the cubes are not really fixed.
No, the cubes are not fixed. You go and you like, I get an integer, I can stop. Okay. You put points, I get an integer, I stop.
Okay, so the cubes are not all the same size?
No, but they have a length scale. They have the same length scale. Okay. But the shapes are like that, you know. They have a length scale, but not yeah, that's a good point, yeah. So you wait until you have an integer, basically, and here you screen what's inside. You put points that are just exactly going to compensate the. So morally, what you think is this, right? You think, okay, if I have too many points on this side of the boundary, then I want to put much fewer on that side, and it will compensate. Right? And if I have too few here, I want to put many more here to compensate. So you sort of balance what was happening inside from the outside. But you see, that's why you need these scales to be quite large, because you want that finding an integer doesn't take you too long, you know, relative to. Okay, so you evaluate how much energy has been added, and you will see that it's essentially this sort of boundary layer cost. And then you want also to know how much volume has been lost. I really mean volume in the sense of the Gibbs measure that integrates dx1, dx2. And that you can also compute. And I have it in my notes that it's of order Rd minus 1 over L, although I don't remember completely why, but I trust my notes. Okay, so now, if you add, you see that you will make an error. Beta Rd minus 1L plus Rd minus 1 over L. And this indicates that there is a length scale 1 over square root beta, which is what you get when you make these two terms equal, where things saturate. So this is a sort of very hand-waving way to find why the minimal scale is 1 over square root beta. You have to have a layer at least of order 1 over square root beta, otherwise you have a less good local law. If you want to keep the same form of the local law, you cannot go below that. Okay, so there is a significant amount of technical work involved in this construction, obviously, but the idea of it is, I hope, relatively natural. So, yes?
You said that, say, the cubes with very bad statistics, so
yeah.
if you have too many points, you just throw them away, but you throw the configuration of the whole thing away, or just the individual cube?
No, you don't throw the cubes. Within each cube, you throw the events that are bad.
Okay.
So it's only some bad events that you throw away, but you still keep the cube. The whole cube is kept. There is no deletion of cubes.
But say when you throw away a bad event, it's not completely independent of what happens in the other cubes, right? If, for instance, if you put all the points in one cube, then of course all the other cubes will have no points. So
yes.
So is that completely local?
Yes, but that's why you will do it will go by bootstrap on scales. You see, because first you know something at the larger scale that tells you that typically points are relatively well distributed in subcubes with a certain precision. And then you go down, you improve your precision, and it tells you again. So you will throw away, if you want, configurations in the whole set. At each layer, you throw away configurations, but their probability is really very small, because it's small in the scale of their size. So originally, what you throw away has probability e to the minus n. So it's really extremely small. Then when you go down, you get e to the minus r. It's a bit less small, right? But you have less and less precision. But you also gain precision from what you learned from your previous scale. So let me try to get maybe into some details of that. Okay. So the first step, in fact, I hope this goes back to your question, Laure, about what are we trying to do? Are we trying to go up in scales or down in scales or what? So we're going to go back to the original question, which is to prove the local laws at the micro scale, right? So back to local laws question. I know that this is true. So with beta over 2, so this is true for R of order n 1 over d. And C, I point out this is independent. So this C is very important. We can call it C, calligraphic C, because it's independent of beta and R. Okay, so this is true from the original bounds I gave you. Now let's try to go to a half cube. Okay, so assume it's true for R. And try to show, so look at what happens for expectation of E beta over 2 F xn Q R over 2. Okay, so let's write this. Let's write this as the expectation of minus beta over 2. So I can have this F Q R over 2 minus beta F xn. So this is the whole space. So I don't know. D. Okay, so on the numerator, I'm going to try to use restriction. in comparison with G. So here what you have really is you're computing, actually I should not write it like that if you allow me. I don't want, this is not quite true. This is the integral of grad h squared in QR. Okay, so this is more clear. You're integrating the same function here all the time. So when you integrate it in this, what is left? Okay, so this thing in the numerator is minus beta integral in QR complement, and in QR over 2 complement, and in QR over 2, it's minus beta over 2. Okay? So I'm just separating, I'm just rewriting the sum of these two integrals. This is the part on the complement, and on inside I have minus beta over 2. And at this level, I can always write that this is less than the one with the V's. You know, the V1 is the one that has the least energy. So I can certainly bound this by minus grad V QR over 2 squared minus beta over 2. So I sort of made them independent in some sense. I separate them. So this is complement. Okay? So I throw away part of the information by restriction, and I compared with the one that has the Dirichlet boundary condition. Okay. Okay, now the denominator. I want to have a bound from above here. So I can use a bound from below for the denominator. So the integral of e to the minus beta grad h squared. You have a question?
V was for the Neumann model.
No, V was for Dirichlet. I think. Yes, no?
Oh, yeah.
Yeah, so this is Dirichlet. So Dirichlet has less energy because I have negative signs. I bound from above. Now the denominator, I want to bound it from below. So I can restrict to fewer configurations because I want to bound from below. So I'm going to restrict to configurations that are neutral with respect to the inside and neutral with respect to the outside. And screened. Right, so I have my inside and my outside, and I'm going to ask that it's neutral here and neutral outside. So what I have here, I have a little combinatorial factor. So also I'm going to ask that this cube is quantized. So it can accept an integer number of points. Okay, so you ask that volume of QR over 2 is an integer. This is not restrictive because you can always, if you have a general cube, you can always put inside a cube with integer volume and outside a cube with integer volume. So you make it quantized, so it can accept a quantized guy. You have a combinatorial factor, and this thing is the volume of the cube. So it's really the ways that you can distribute the labels of your particles, knowing that you have n bar particles here and n minus n bar particles outside. So this is the number of labelings of your partition. And then you integrate e to the minus beta grad u QR over 2. You separate variables. Okay, so this is to the power n bar, and this is to the power n minus n bar. So why can I bound like this? Because I have my projection property here. I can always bound this from above by the sum of the Neumann energies. So if I bound this from above by the sum of the Neumann energy, I bound this thing from below by the sum of the Neumann energies, and now these two things become independent. So this is by projection property, if you want. Okay? So in the denominator, I compare with the Neumann guys by subadditivity of the Neumann energies. And the numerator, I compared with the Dirichlet guys by the superadditivity, if you want, of the Dirichlet energies. So if I go back to my question here, I'm going to have in the numerator, I'm going to have to sum, depending on the number of points that fall inside my cube here, which will be called little n, the number which fall outside. And I'm going to have my L big N in the complement, and my Ln in the set. So here I have to decompose over all the scenarii of how many points fall here, how many points fall outside. So I have all these possibilities. And this time I don't know, I don't have a choice, right? And I can bound from above by that. So this is based on the upper, the computation on top. And in the bottom, I have the computation with the ideal number of points. And now I have k. So there is something I forgot. Which is that up there I have one with beta over 2. So this one is with beta. And this one is with beta over 2. This is the place where I lose a half beta because I want to find the local loss with beta over 2. So it deleted a beta over 2 here. Otherwise, everything else is beta. Okay, so you split your events. How many points fall inside, how many points fall outside. You make a comparison with the Dirichlet problem or with the Neumann problem, and you find some big ratio like that. Yes?
And I don't get it with n bar.
So n bar, that's the ideal number of points in QR over 2. It's the volume. Because in the Neumann problem, it has to be neutral. So you don't have a choice of how many points fall here.
Yes.
You can only have n bar. Whereas in the other case, you have a choice. Okay, so now what you have to do is you have to work a little bit. You have to say, okay, I have some initial rough estimates that tell me that n concentrates near n bar. Because I know that my concentration estimates tell me that if I had a too much deviation of the number of points here, I would have a very large energy, and that would be contradictory with my law at the upper scale. I assume that this is true in R, so I already have a very good estimate with that. Okay? So I can throw away the events where n is not very close to n bar, and you can actually estimate it in terms of, you know, little o of RD, at least certainly your errors. So you can throw away many things in your sum here. And so for the sake of presentation, let's think of little n as being equal to little n bar. Okay, now you remember that with screening, we prove that log ln is like log kn up to an error which, okay, you know, there is this error rd minus 1l. Small errors, okay, small with respect to the volume. So formally, I can cancel this and that. Formally, I take only one term in the sum, I cancel. And now ln and kn, here, they're almost the same. So these things, it's 1 up to basically these small errors, which are little o of RD divided by RD. Okay, so here I should explain one thing. Now we're talking about an exterior domain. Right? I'm working in an exterior domain. I have a small cube here, and I want to compare the free energies here. But what you do is you screen near this boundary. Right? You're going to do the screening from the other side. So instead of doing it from the inside, you're going to do it from the outside. And the price to pay for the screening is a boundary term, but it's the boundary of this small thing. So even though the region here is very large, what matters is the size of its boundary. So you do make an error which is negligible with respect to the volume. Okay, so if you do that, you find that eventually this is like that, this is like that, and what is this? This is like kn. So with the twiddle, it's like k beta over 2 qr divided by k beta over of qr. So you don't have the same beta. But now we have a priori bounds for these guys. Whenever we have a k, because I told you at the beginning a priori bounds in a thing of size n, but you have the same a priori bounds in a thing of size r. You just have fewer points. So the log of that. So the log. Okay. Maybe let's finish here. The log of the expectation of this is going to be like the log k beta over 2 k beta of qr plus, I told you, little o of rd, and this I can bound by c beta rd plus little o of rd. So this thing is more precise than that. It's my it's this. So these are like a priori estimates.
K beta over 2 qr
over 2, yes. Okay, so when you examine everything carefully, you find that if you start from this law at the bigger scale, what this has helped you do is it has helped you rule out all the very deviant scenario where you would have a number of points that's delirious compared to n bar. That gets ruled out. It also helps you say that most configurations are screenable, because you need good estimates to be able to screen. So from this information at the higher scale, you screen, and you get to a lower scale, and you can check that this C can be made less than the original C. So you have not worsened your constant here. Otherwise, the thing would be a bit useless. Otherwise, you would bootstrap, and at the end, you will have nothing. And you check that you saturate at this minimal scale, where here, otherwise, you get too big of an error. Okay, so this proves the local laws. And now that we have that, we can go back and look at this rate of convergence of log k and log L. You know this picture with the two quantities that were going like this and like that? Because now we have learned a lot of things. We have learned that down to micro scale, I have an energy proportional to the volume in a given volume. So in particular, I can go back and look at my boundary errors in the screening. You know, the energy that was really here is really proportional to the volume, so I can optimize my L. I can make L equals 1 or equals 1 over square root beta. And then I can see what happens when I have a big box and I cut it into 4, let's say. So if I have a big box, I want to compute the K of the big box. I can compare with the K of the smaller boxes by screening. Because if I have my big box, I can say, OK, here maybe I don't have the right number of points. Maybe I don't have the right number of points. But I can screen. I can screen, change my configuration here, here, here. And I know how much error I will make. OK, so this thing, basically, if I call that phi of r, you will find that phi of r is equal to phi of r over 2 plus a little o of, actually an o of 1 over r. So this is by screening. Now you iterate that. So whenever you double, you add an error like that. So you have to make a series, I think. So you iterate that. And you find that phi of r equals phi of infinity plus O of 1 over r. So now you do it the other way. You go up in scales. It says that when you go up, you can compare with, at each scale you can compare with the lower scale. So it tells you that you converge at speed at most 1 over r. So it gives you this thing, which is a theorem in itself. And I should stop. So together with these local laws, at the same time, you see by the same process, we've obtained theorem. So now this is for the Neumann guy in the cube. It's equal to some limit plus O 1 over R. So in fact, there is something that depends on temperature here that's explicit. But okay, so tomorrow we'll get an expression or variational formula for f of beta from the separately, and then we will deduce an expansion for log z for the original problem, because this is a sort of side problem. But you can go back to the original problem with that, and you can deduce CLT for fluctuations in 2D at least. So this is all the Coulomb case. Huh? You've seen how Coulomb has come at every turn, because every time we solve these Laplace's equation, we're using the fact that it's the Coulomb interaction.
That's all for today.
Yes,
Thank you very much.
enough for today. Sorry.